Okay, let's talk about error handling. It's absolutely critical in any software project. Basically, error handling is all about proactively thinking through what could go wrong while your code is running and then having a plan to deal with those situations gracefully. It's not just about preventing crashes, it's also about giving users clear feedback if something unexpected happens. Think of it like a driver carefully navigating the road. They anticipate potential hazards and take steps to avoid them. Error handling improves stability, makes the application more user-friendly, simplifies debugging, and ultimately builds a more reliable program. Okay, let's talk about errors and exceptions. Essentially, an error is when your code has a really big problem, something that prevents it from running at all. Think of it like a broken foundation for your program. You'll often get a specific message telling you exactly what went wrong, like a missing semicolon or a type mismatch. Now, an exception is a bit different. It's more like an unexpected event. Maybe you try to open a file that doesn't exist, or you divide by 0. Your program can sometimes handle these gracefully using something called try-catch blocks. The key thing is, exceptions don't always cause your whole program to crash. They give you a chance to deal with the problem and keep going. Okay, so let's talk about common errors you might encounter in Python and really any programming language. We've got a few key categories. You'll often see type error popping up when you're trying to do something with the wrong kind of data. Think about accidentally adding a string to a number, for example. Then there's value error, which means your function received the correct type of data, but it just isn't valid, like passing an invalid date format. Index error is when you try to reach beyond the end of a list or tuple. Key error happens when looking up something in a dictionary that's not there, and file not found error. Well, that one's pretty straightforward. Finally, we have zero division error, which is just trying to divide by 0, a classic. Recognizing these types will help you write more robust code. Okay, let's talk about how I approach handling errors in my code. It's all about building apps that don't just crash when something unexpected happens. First, I think about where potential problems might pop up, like if a user enters bad data or we can't find a file. Then, I use try-except blocks to catch these errors specifically. Instead of catching everything with a general exception, I try to grab the specific type of error that occurred, so I know exactly what's going on. It's really important to log those errors, including details like when they happened and any relevant information, so we can debug later. And finally, if I can't fully fix an issue within my function, I might re-raise the exception with a little more context for someone else to handle further up the chain. The key is making sure the application keeps running smoothly, even when things go sideways. Okay, let's talk about try-catch blocks. They are a really important tool for writing reliable code. Think of them as your program's safety net. A try block is where you put the code that could potentially cause an error, like dividing by 0 or trying to access a non-existent file. If something goes wrong in there, if an exception happens, the program doesn't just stop abruptly. Instead, it jumps over to the catch block. The catch block is where you tell the program what to do if that error occurred. You can log the problem, display a helpful message to the user, or even try to recover from the situation. It's all about preventing crashes and making your application more robust and user-friendly. And in JavaScript, like in the example I'm showing here, you can see how simple it is to set up. Okay, let's dive into the finally block. It's a really important piece of exception handling in many programming languages. Basically, whenever you use a try-catch structure, the finally block always runs no matter if an error happens within the try part or not. This is super useful for things like closing files or database connections, making sure we don't leave resources open and potentially causing problems later on. It's also great for logging important information, so you have a record of what happened, even if there was an error. Okay, let's dive into structured exception handling. It's all about creating a really organized way to deal with errors in your code. Instead of just throwing catch blocks everywhere, this approach sets up a clear hierarchy of handlers. Each handler is designed to specifically manage an error based on its type or how serious it is. It's like building a roadmap. Each handler knows exactly what it needs to do when something goes wrong. We have catch blocks for specific errors, and finalizers that make sure everything gets cleaned up, even if there's an issue. This makes your code much easier to read, debug, and generally more reliable. Okay, let's talk about checked versus unchecked exceptions. Think of checked exceptions as the ones you have to deal with. A compiler basically says, hey, this could go wrong here, handle it. They often represent problems that are relatively easy for the code calling your method to fix, like a file not being found. Unchecked exceptions, on the other hand, are more like accidental mistakes in your code, such as trying to use a null variable or passing an invalid argument. You don't have to specifically catch these, but it's still important to be aware of them and write code that handles potential issues gracefully. Okay, let's talk about designing robust error handling for really large systems. It's not enough to just catch an exception and log it. We need a layered approach. Think about how errors might manifest at different levels, the application itself, individual services within your system, and even down to the infrastructure. It's also important to handle specific error types. Don't treat everything as a generic something went wrong. For example, if you have a database issue, you can identify that specifically. And finally, always consider graceful degradation. What happens when something fails? Can we provide helpful feedback to the user instead of just crashing? Okay, let's talk about error propagation. It's a really important concept when we're thinking about how code handles problems. Basically, imagine an error starts in one part of your code, say like trying to divide by 0. It doesn't just stop there, it bubbles up through the functions that called it until someone actually catches and deals with it. It's like a ripple effect. If you don't handle these errors, you can get a Stack Overflow, which is a serious problem because it means your program went into an infinite loop trying to figure out what went wrong. Different programming languages use different ways to manage errors, but the core idea is always the same, propagating those errors up until they're dealt with. Okay, let's dive into global exception handling. It's a really important technique for building reliable applications. Basically, it means having one place in your code, usually at the very beginning, that catches any unexpected errors that pop up anywhere else in your program. This is useful because it creates consistent error reporting and makes debugging a lot easier. Imagine you have an error happening somewhere deep inside a function. With global exception handling, you know exactly where to look when something goes wrong. It's like having a central control panel for all errors, ensuring they are logged and handled in the same way. Okay, let's talk about logging errors effectively. It's not enough to simply say an error occurred. You need detailed information so you can actually figure out why it happened and how to fix it. Think of your logs as a detective's notes. The more details, the better. Start by making sure your messages are specific. Include things like user ID or request parameters that help pinpoint the problem. Next, consider using structured logging, which means formatting your log entries in something like JSON. This makes them super easy to search and analyze. Then, utilize different logging levels. Debug for detailed info during development, info for general operation, warning for potential issues, error for actual problems, and fatal for critical failures. And don't forget correlation ID. These help you track related events across your application if something goes wrong. Finally, ship all those logs to a centralized system like ELK or Splunk. That way you can easily search through them and keep them stored for the long term. Okay, let's talk about stack traces. A stack trace is essentially a detailed log of how your code got to the point where an error occurred. It's like a timeline showing every function call that led up to the problem. It tells you exactly which functions were involved and shows you the line number where things went wrong. So it's incredibly helpful for figuring out the root cause of the issue. Basically, by looking at the stack trace, you can work your way backward through the code to identify where the error originated and understand any dependencies that might be contributing. Okay, let's talk about debugging tools. They are absolutely essential. First and foremost, browser developer tools like Chrome DevTools or Firefox DevTools are my absolute favorite. They let me dive into the code, inspect elements, see what network requests are happening, and even step through JavaScript line by line. Then I often use logging libraries, whether it's just console log for simple debugging or more sophisticated tools like Winston to create structured logs that make it much easier to find problems when things go wrong in production. Debuggers within my IDE, like VS Code's debugger, are also incredibly helpful. They let me step through the code and examine variables as I go. And don't forget about static analysis tools. They can automatically catch potential issues before they cause runtime errors, helping you write cleaner, more reliable code. Okay, let's talk about dealing with errors in asynchronous code. It can be tricky because you don't know exactly when an error might pop up after a function is called. A good strategy is to use try-catch blocks inside your promise chains. Think of it like this: you're wrapping the potentially problematic parts of your code. Also, consider an error-first design where functions always return a promise that either gives you the result or an error object if something went wrong. When you encounter an issue, reject the promise with a clear message on any relevant data. Then, when using async/await, remember to use try-catch around your await expressions. They are still relying on promises. Finally, for more complex apps, look into centralized error handling to catch errors consistently across different parts of your code. Okay, let's talk about defensive programming. Think of it as a proactive approach to writing code. Instead of just reacting when something goes wrong, which is what traditional error handling often does, we build in safeguards before the problem can even arise. It's like anticipating potential hazards and taking steps to avoid them, just like wearing a seatbelt before driving. Defensive programming directly relates to error handling because it significantly reduces the number of errors that need catching in the first place. We do this through things like checking our inputs, making sure they are valid, handling null values gracefully, and considering those tricky edge cases. By doing these kinds of checks up front, we make error handling much easier and more reliable. Okay, let's talk about two really important design strategies for dealing with errors: fail fast and fail safe. Fail fast means we want to catch problems as soon as they appear. It's like a quick warning sign that tells us something isn't right before it causes bigger issues down the line. We stop processing immediately. On the flip side, fail-safe is about keeping things running smoothly even if an error pops up. It's all about gracefully handling problems and not just shutting everything down. It tries to recover or gives us a reasonable alternative, like retrying a database connection, for instance. The core difference is that fail-fast stops processing, while fail-safe keeps going. Okay, let's talk about input validation. It's a really important concept for building robust applications. Think of it as a gatekeeper that checks everyone coming in and making sure they are allowed access. Basically, we want to confirm that the data we get from users is actually what we expect it to be. Numbers are numbers, emails are emails, things like that. We do this by checking the type of input, if it's within a reasonable range, whether it follows a specific format, and making sure required fields aren't missing. And when you validate before doing anything with the data, you can avoid lots of problems down the road, things like errors crashing your program or even security vulnerabilities. It's all about preventing those issues from happening in the first place. Okay, let's talk about keeping an eye on things when your application is live. It's not enough to just build it. You need a system in place to catch problems before they become major headaches for your users. We want centralized logging, basically collecting all the messages from every part of our app into one easy to understand location. Then we set up monitoring and alerts, so if something goes wrong, we're immediately notified. Error reporting tools can really help us understand why things are failing, providing context like who was using the application at the time. And finally, having health checks and rollback mechanisms gives us a safety net. It's all about being proactive and keeping things running smoothly. Okay, so when asked about debugging techniques, think about your process. It's really important to be able to reproduce the issue first. That's key to understanding it. Then a good strategy is to break down large problems into smaller chunks and test each one individually. Logging can be incredibly helpful. Use different levels of logging to track what's happening. Don't forget about your IDE debugger. Stepping through code and inspecting variables can save you tons of time. And sometimes, just explaining your code out loud to a rubber duck can reveal a logic error you might have missed. Okay, so let's dive into breakpoints. Think of them as little markers in your code places you want the debugger to pause. When a breakpoint is hit, it stops the program so you can take a closer look at what's happening. You can then examine variables and see exactly where things went wrong, which makes debugging much more efficient. It's like having a magnifying glass for your code. Okay, let's talk about step-through debugging. Imagine you're driving a car and it suddenly starts acting weird. Maybe it stalls or swerves. Step-through debugging is like having a really detailed dashboard that lets you watch every single action the engine takes, one at a time. You can stop the program after each move, each line of code, check what your speedometer variables are showing, and see exactly where things started going wrong. UI like VS Code or IntelliJ provides tools to make this process super easy with buttons like step over, step into, and step out. It's a fantastic way to really understand how your code is running. Okay, let's talk about debugging memory leaks. A memory leak happens when your program keeps holding onto computer memory that it no longer needs, kind of like leaving the lights on in a room you've already left. This can slow down your application and eventually cause it to crash. Common culprits include not closing connections or forgetting to release resources, or even tricky circular references between objects. To find these leaks, we use tools like memory profilers, which track where memory is being allocated and delocated, and leak detection libraries that help us spot issues. Code reviews and static analysis can also be really effective, just looking for clues in your code. And as a reminder, preventing memory leaks in the first place through good coding practices is always the best approach. Okay, let's talk about logging levels. Think of them as different ways to communicate with yourself and potentially other developers when something happens in your code. You've got info, which is just general information like the user logged in. Then you have warn, which flags potential problems. Maybe a value is out of range, but the application can still keep going. Finally, you have error, and this is where things get serious. It means something went wrong that needs immediate attention because the app can't continue without fixing it. When choosing levels, start broadly with info to understand your program's flow, then use warn for recurring issues, and reserve error for truly critical failures. It's all about prioritizing what you need to know.